Howdy Lockslings, and welcome to part 1 of my Scratch Evolution Simulator series. In it, I will take Scratch, a drag-and-drop programming language intended to teach young children how to code, and design an evolution simulator similar to Primar's Evolution Simulations series. The way it will work is, at the start, 10 scribbles will be created. They will all forage through bushes to find berries. They move completely randomly, and if they find a bush they gain energy. If they don't, they lose energy. Each scribble has different attributes, such as how well they can memorise the bushes to return to them. The scribble that survives the longest has 10 children, each with slight random variations or mutations, then dies. The cycle repeats with those 10 children, the thought being the scribble who survives the longest will have the best statistics and therefore be the best launching off point for the future generations. And as the standard gets higher, it forces the scribbles to get better and faster or else they die. Going back to the memory example, more memory means they'll consistently be able to find a valid tree at the expense of being less likely to branch out and find trees with better contents. So where's the sweet spot in this situation? Well, I don't know. That's for the simulator to find out in a later episode. In this first video, I'll create a backpackable layout that creates 10 scribbles which each try to generate the highest number, with the attributes being the lowest possible number and the highest possible number they can generate. Obviously it's best for these both to be as high as possible, but this is a proof of concept and we need an easily trackable success criteria. So, without any further ado, I think we'd better begin. This is the Evolution Simulator proof of concept, and after masterfully drawing this scribble, let's get coding. I put the spawn clone script in a run without screen refresh block just to add some extra coolness to the code, and this script makes them line up in a lineup. Wait. Oh, I forgot to make it run without screen refresh. Oh wait, I forgot to hide the original guy. Wait, that doesn't line up. It all works perfectly if we add a +1 here. Oh, but wait, that means the number of clones doesn't actually reflect the actual number of clones. Well, maybe this value only needs to be 1 more than this value, in which case the same effects would be achieved by subtracting 1 here. Okay, that works. Now for the clones, and as I type this variable, it seems like a good time to mention that my mouse is invisible in all of this footage. For the longest time I couldn't get the mouse to show up on OBS. Okay, some variables. We need to make them for this sprite only so each clone can store and change their own values. These values are the highest upper bound and the lowest lower bound. The clones will choose a random value between these two numbers, but actually the lower bound could go higher than the upper bound and nothing would change, so there's no point trying to stop that, so we'll just change their names to value 1 and value 2 from now on. Okay, so when they start as clones, they'll wait a bit. This is less important for the first round, as we used that run without screen refresh block, but as the clones may be spawned soon on different ticks and on different parts of the cycle later in the game, this is important to make sure it's not all offset and to make sure that they're all competing at the same time. However, there's an issue here. If we want this evolution simulator to work efficiently at all, then we need to make it turbo mode friendly. Turbo mode, not to be confused with turbo warp, is a mode in Scratch achieved by shift-clicking the green flag, which causes the game to run at very fast speeds. But some blocks, specifically these ones, aren't affected by this and still run at their usual sluggish speeds. So how do we make a timer that activates every 1 second in regular mode, but is able to run faster in turbo mode? Well, Scratch is coded to run at 30 frames per second, which means the screen can refresh 30 times per second. The most common way to force a screen refresh is to wait 0 seconds, but for some reason I couldn't get that to work in the turbo mode tests. I also thought I could use a run without screen refresh block, but there was no luck, because run without screen refresh doesn't necessarily mean it forces a screen refresh. Instead it means the exact opposite. It means the entire script will run in between screen refreshes, and this can also apply to large clusters of code so long as none of them force a screen refresh or longer. So this was the problem with most blocks I tried, but there was one thing I could do. Well, we will need this to repeat 30 times per second, and if we use a repeat loop, it refreshes after every loop, I think. But it doesn't work with just an empty repeat script, so the thought was, if this universal timer will run in the main non-clone script, who is hidden, what he does won't matter. So I could really just make it perform any block. I chose to make it show then hide in this script, and as I mentioned earlier, this entire cluster will run in between screen refreshes, so we won't be able to see him appear on the screen for a single frame at all. Okay, perfect, the timer works. And I'd like to note here that later I decided to change this for efficiency because it uses 2 blocks and it technically would be more efficient to make it only perform 1. So I changed it to a go to position block, but it didn't work and the timer worked similarly to when the script was just empty. So I replaced it back to the old version, and the reason I think that happened is because after the script has already run a few times, it will just be going to the position it's already in. But anyway, on with the script. I also coded some other more important scripts. We have the clones generate a number between their values, which are randomly applied to each one in the clone script, and randomly altered when the clone is created. So the evolution and mutation stuff works. Then there was some pretty difficult coding to figure out which clone got the highest results. We as the viewer can see each scribble's value because they're saying it, but they're all stored in for this sprite or clone only variables, which only this sprite or clone can access. They can't see other clones' variables, and other clones can't see theirs. And it wouldn't work if all of these variables were accessible, as I mentioned earlier, so I came up with this script. Each clone's result is added into a for all sprites list. Each wave the list is cleared, and after all of the results are added, each clone goes through each value one by one with an index variable. That is terminology for a variable that increases every time it loops around. And if their result is equal to or over the one they're measuring, they're allowed to continue. If not, they die. Once that loop is finished, if they're not dead, they have 10 children. This was the point where I abandoned the line form and made them go to random positions. It might work if we used the preset block we made, the run without screen refresh one, but it was a part of a larger issue, and so it would be easiest if the clones would just be spawned in a random position. So what is that issue, I hear you ask? Well, it was this. How do we handle ties? Well, I'm going to answer that in the form of a story. This was not the first time I tried to record this evolution simulator footage. It's also the third time I've tried to record this audio. It was in fact the 5th recording of the footage. The first one was a couple of years ago. I knew a lot less about coding, but next was about 3 days before I recorded this footage, but I deleted it. I think it was because it was bad, but I can't remember exactly. Then there was another one on the same day. It got deleted because of this thing that says it's unable to save. So I coded another one before realising that the entire evolution simulator that I was using didn't work that well anyway. The way it worked was each character had energy that depleted or increased dependent on whether they found a bush, but anyone who got over 10 energy halves their energy and has a child. I couldn't get the variable balancing to work, and the footage was really awful as I just spent half of it changing variables and desperately trying to get it to work on camera. Since then I've had a few more ideas to make it better and changed it into that version I said at the start. Anyway, this all matters because I had a variable tracking the number of clones by adding a change clones by 1 in the when I started the clone script. It would always stop at 290, sometimes flickering down to 289 for a few ticks. I eventually realised it was because clones in Scratch can only add up to 300, and 10 of them were taken up by the bushes. But I was interested how, because of how I implemented the counter, it would always reflect the actual number of clones. But in the first version from years ago, the counter would go over 300 as it was before the create clone blocks instead. If a clone exists, it can add a variable. If it is deleted and doesn't exist, it can't. I know that seems very obvious, but either way, after the massacre, the surviving clones will increase a winner's variable, and the dead ones will not because they don't exist anymore. And then each of those surviving clones will create 10 divided by winner's clones. You might be thinking that this wouldn't really work if there were 3 clones, and you're right, but even if there are a different number of clones in one generation, it will eventually get fixed out when there are 1, 2, 5 or 10 winners. So, cool, your opinion doesn't actually matter, and I was right all along. Now let's analyse how this proof of concept works. And it works. Those numbers are increasing. 12 is indeed bigger than 11. This is great. Turning on turbo mode, and yep, that is definitely faster, and the numbers are still increasing. I added a feature to see what the clones value 1 and value 2s were, and a variable to alter how many clones were allowed. I added a feature to toggle between seeing what the clones' numbers they were outputting were and what the 2 values they were choosing between are, and my thought at the time was more clones will allow for more development more quickly, with the only expense being increased lag. But there was an issue. The clones would clearly favour the upper bound and leave the lower bound to dwindle, sometimes going into negative numbers, and all of the clones could rely on just getting lucky with the highest number. Having too many clones creates too big of a safety net, and now they can just rely on luck. It does seem to fix the more you run the scripts, but slower and less severely than the upper bound. So I tried doing it with some lower clone numbers in a separate recording because I didn't think of any of this at the time. So I added this script, taking advantage of the facts I showed earlier that these blocks still run at regular speed in turbo mode, and decided to run different tests and record the final results. I'll take the averages of 2 tests to try and remove randomness, and the timer will always be 50 ticks. I'll have 2 tests where they constantly show the random number they're choosing, and 2 tests where they show the numbers they're picking between, and I'll do it with samples of 5, 10, 25 and 50, and the timer will always be the 50 ticks. The more clones there are, the larger tick offset there'll be between the clones being created, and they'll be more likely to be spawned between cycles. So as the number of clones increases, you need to increase the timer by a bit. Now the issue can be fixed by making it a run without screen refresh, and that might work, but honestly my code involving turbo warp timing has been pretty unreliable today, and we still can't change the timer even if that is the case, as that will mean that some tests will have a faster time and it will result in a larger number as it has more iterations to evolve, and that is an unfair advantage. So here are the results of the experiment. Okay, so I was incredibly excited when I saw the lower clone samples developed just as fast, if not faster than the samples with 25 or 50 clones, but it doesn't appear to have as much of an effect on the lower bounds. I had an original section in my scripts explaining why this could be, but it was pretty bad because I couldn't actually think of any reasons why it might be, and I was just saying, ooh, well maybe the values are weird. But I decided to record one more sample with just 2 scribbles, the minimum necessary as you can't determine a best when there's only one option. And after I'd already tested it without recording to avoid looking like even more of an idiot on the internet than necessary, Tusky? Is Tusky outside my room? That was definitely a Tusky whimper. Also, is GarageBand still recording? Is it Tusky? How have you got some back again?
Salad.
Hi, Tusky. Tusky, make a cute noise into the microphone. No, I didn't say scratch the microphone. Tusket's my little puppy, and the stairgate was supposed to be closed, but apparently she's climbed all the way up the stairs to my room, which is at the top of the house. And now she's digging into my chair. How are you, Tusky? Are you going to be quiet? I'll record the rest of it later. Now, some of the simulations going by might have large lag spikes like this, but that doesn't necessarily matter as it affects the entire code equally, so the development pauses, but so does the timer, so there isn't any overall effect, I think. Also, it can be partially fixed with a site such as Turbo Warp, not to be confused with Turbo Mode in the future. Anyway, this definitely works, with similar numbers and much higher results in both values. The testing, I suppose, just wasn't thorough enough last time. It also works with 3 scribbles. So overall, I'm incredibly happy with how this turned out. Whilst I didn't do anything a human-made algorithm couldn't do much better, it shows that competitive simulators can help in producing reliable results, and this code will serve as a handy structure for all future projects I make involving evolution. In the next video, I'll apply some of that more complex context and introduce more conflicting attributes with more abstract and uncertain trends. It sounds very complex and scary, but it's really just a lot of these things running at the same time. They'll be running to find the perfect value that balances out the upsides and downsides, and that's really what this one's been trying to do, except there are no downsides, so the balance of the upsides and downsides is just infinity, and therefore the goal that they're all trying to get the value to is infinity. But in the future, that value might be something like 18.62859, and therefore they'll be trying to get it as close to that as possible. I did try to create a separate version with this idea of trying to get as close to a value as possible, where they evolve to get in a position as close to the mouse pointer as possible. It was coded much more quickly than this one, and there are a few issues which I managed to fix. But overall it also works pretty well. Originally they could have gotten stuck on the edges, And I think the reason that happened is that the variables representing their positions can change because they need variables in order to randomly change it. And if they're on the edge, they just get squished against it and can't go beyond it. So if the edge is at, say, 240, they can evolve to go to 255. And then if a clone goes to 240, whilst it should be closer and favouring that would allow them to get unstuck on the edge, because of their actual scratch positions, it would think that they're the exact same horizontal distance, and therefore it wouldn't survive, and they'd only judge the vertical distance, making them often just get stuck on the edges. The way I fix this is by switching it to a larger costume before it changes position, and then switching it back. And another thing to note is that they might not always necessarily be travelling towards a fixed point, because the point can change based on different outside variables, such as the frequency of the food, how much time has passed, and the behaviour of other creatures in the simulator. So,